Hi, welcome to Aristothink. Today you're going to see a friction problem, another one, and on this one we have this object, we have this base, it's like this, and I'm going to pull this base. I want to pull this base and the object is going to slide and fall. But I want this object to fall. This is the object. I'm going to pull this base to the right, and I want to see what is the acceleration I must put on this base such that the object is going to fall inside the container. Now, just pay attention to something. What is the minimum acceleration? Well, if the acceleration of the base is very little, what's going to happen? Nothing. There is no sliding. Slide is not going to occur. So if I put it very fast, that is not the problem. If I put that very fast, the object is going to fall pretty close to the center. If the acceleration is almost nothing, I can pull forever and the movement is never going to occur. So that is not an option. So I must pull this base with a certain acceleration such that there is a sliding, but the acceleration must be at least at certain value that the object falls inside. So this is a problem. It's a very interesting problem, this one. So the first thing let's read the problem. So what is the minimum acceleration? The base, this is the base, must be pulled so that the object falls inside the container. So this is the container. We have this base. This is the base. This is the object. I'm going to pull this base with some force. Let's say force U. Force U is your force, the force you're going to pull this base. So the first step, well, what we have to do, we have to see what's going on this object. The first thing is let's draw the free body diagram. So we have the base, the object. Now the base is moving to the right and the object is moving to the left relative to the base. So do you agree that as the object moves to this direction, is going to move towards the end of the base? Well, there is a friction, and the friction is always opposing to the movement. So if the object is moving to this direction, the friction is in here. So this is the F friction for the object. And there is a force in here, is going to be the Fu, the force you pull the base. Now, let's stick to the object. Well, what is the net force? Need more space, so what's going to be the net force? F net. On the object, mass times acceleration. This subscript is O for objects. What is the net force in here? Is the frictional force. It's going to be mu. And I have mu k and mu s. So this is for the static friction, the kinetic friction, or the dynamic friction, the movement. Of course, I give all this. It is up to you to see which one you're going to use. Is it going to be the static friction or the kinetic friction? The kinetic, right? It's the movement. So it's going to be the mu k times normal, mg, times mass times acceleration of the object. Mass cancels out, so I have that the acceleration of the object is going to be mu k times g. So this is the acceleration of the object, and this acceleration is going to be constant. But now let's take the opportunity to see the charge of friction against Fu. So if we could draw something. This would be the friction force on the object, and this would be the force on the base. This is Fu. Well, it's going to be like that. Maximum, fall, and then come. Now, it's very important that you understand this charge. So this is 45 degrees. in a way that if I pull with, let's say, if I pull the base with F1, well, the friction force is going to be exactly the same force. The friction force, until it doesn't reach this threshold, the threshold is the maximum, whatever is the force I pull something, the friction is going to mimic that force. And the friction is going to be exactly the same force opposing. The friction is just an opposing force. And it goes exactly the same magnitude, opposite direction, until it reaches this threshold. So as I increase my FU, my friction is going to increase, opposing exactly, so maintaining the object is stuck to the base. But there is going to be a moment where this is going to be mu static, mu as normal. And this is the maximum friction force. And after this threshold happens, the friction falls slightly a bit. At this moment, movements, sliding starting to occur, and then we go into mu kn. So the friction we're going to use is mu kn. Why? Because this is the movement. So in here, up to this part, no movement, no movement. And from here and onwards, from that moment onwards, sliding occur. So you just have to understand what's going on. Now let's see what's going on with this acceleration. Well, this is acceleration that the object is going to have. Now, what happens if the base has an acceleration exactly this? Well, if the base acceleration, so if the acceleration of the base is, let's say, smaller than this, is smaller than a object, what's going to happen? Well, the object is not going to move, agree? There's not going to be any movement. So, no movement. No sliding. It's going to move because it's going to be stuck to the base. So, no movement, no sliding. Now, what happens if the acceleration of the base, it is exactly this one? That is going to occur, movement is going to occur. So whatever is the acceleration of the base, if it is bigger or equal than this acceleration, then sliding is going to occur. But there is a but. So the minimum, the first idea would be this. Well, what is the minimum acceleration of the base? Oh, the minimum acceleration is exactly mu kg. No, it's not. For this is the minimum acceleration, so sliding starts. But sliding occurring is not enough. Is not enough to make the object falls inside. Well, it can slide, but it can fall outside. Maybe it can fall in here. And I want the object to slide fast enough so it falls inside. So acceleration of the base must be a tiny bigger than this. So we have to consider another condition. So there are two more conditions that we have to assume. The first one is this. The object. So the object must move B, these parts. B mirrors. Agree? I'm trying to get the worst case scenario, and the worst case scenario is the object must move exactly B mirrors. So let's go. We have from kinematics equation, we have delta S is going to be V0t plus AT squared over 2. So what is delta S? Is B. Is going to be, this is 0. Acceleration is the acceleration of the movement. Now notice something. Once this block moves, it can only move under this acceleration. There is no way it's going to move in any other acceleration. This is the friction force friction force depends on mu k, which is constant, on the mass, which is constant, and also on g, which is also constant. So acceleration, it is absolutely constant under this situation. And the acceleration of the block is always mu kg, always. So if the block must move b meters and has an acceleration of mu k g, what's going to be the time is going to take to do this? We have an acceleration of the block, we have a distance, it must move, so how long is going to be? If we do this, so what's going to be? I'm going to leave as t squared, I'm not going to take the root, you're going to see why. So this is going to be what? 2b divided by mu k times g. So this is the time for block reach the right wall of the container. Agree? So it's going to be exactly in here. This is worst case scenario. Now there is another situation we have to consider. Very important. Well, while the object has to move from here all the way to here, in order to fall, the base, this part, the end of the base, must move from this position up to this position. Can you see this? So the base, the object must travel only this, but the base must travel from this part up to here. Why? Because I want to see a situation where the base is going to be pulled all this way and the object is going to be falling actually a tiny bit. Like this, you see? So the base must be exactly at the end of this wall. So the object falls. But the object is only going to fall when it's going to be at the very end of this base. And the very end of the base must be at the end of this wall. So this is very important. Let me just erase this. Now the other condition, and then it's over. The problem is basically over. Now the other condition is, so the base must move. Now what? Think for a moment. How much must the base move? A, B, to A, to B, what? Think for a moment. Pause the video, pause. I want to know how much in meters must the base move? If you said A plus B, you are correct. It must move A. This is B, isn't it? So must move A plus B meters and something else. Must move this and exactly on that time. Agree? Because this is the time the object is going to be in here. By the time the object be here, the end of the base better be exactly in here. So, and also in t seconds. Okay, that's it. Now the problem is solved. Let's use again the same equation. So delta S is going to be V0t plus A t squared over 2. Now, what is delta S? This is for the base. What is the delta S? The base must move this. This is the displacement, A plus B for the base. This is 0, of course. Now, the acceleration of the base, I don't know. That is what I want to know. What is the minimum acceleration of the base? So, let's say acceleration base. The time, exactly this. Exactly the time the object is going to take from here to here. The time is as 1. You see, that's why I never took the square roots, because this is time squared. So I'm just going to substitute 2b over mu k times g, and the half. Now this cancels, so acceleration of the base is going to be, this is worst case scenario, is going to be, so it's going to be AB, A plus B, divided by B, times mu k times g. So this is not the answer. So this is the worst case scenario. Worst case scenario. This is worst case scenario. Now, remember, if I pull the base with a very little acceleration, the object is not going even to slide. If I pull the base with this acceleration, which is the acceleration where the blocks moves, so slide is going to occur. Beautiful. But that is not enough to make the object go fast enough and fall inside the container. So it must be a little bit bigger than this one, so it can fall inside. So this is the threshold. This is the minimum acceleration it can happen. If this acceleration, this is B for base, sorry. If this acceleration of the base is going to be smaller than that, but bigger than this, sliding will occur, but the object is going to fall outside. So if the object must be exactly this or bigger than this, then slide is going to occur and the object is going to be inside. So the final answer is this: the acceleration of the base must be bigger or equal than A plus B over B times mu k times g. This is the problem. This is the answer. So you see, in a nutshell, the problem is this. We have the object, we have this friction. If you pull too fast, beautiful, it's going to fall straight inside. If you pull too slow, not even. If you pull too slow, lower than this, friction is not going to happen. So, I mean, friction is going to happen, but sliding is not going to occur, and there is no movement. If you pull with a force, with this acceleration exactly, sliding is going to start, but it might take forever to fall. We want acceleration to be fast enough so it falls inside. But what is the minimum acceleration that we can put? So for that, the object must go up to this point. It must move B. This is the first condition. For that, it needs this time. And the acceleration is always this. You have to remember this. The acceleration for the block is always this one. It's never going to change. So it's a fixed acceleration. We have a fixed displacement, so there is a time. Now, another condition. While the block goes under this displacement, the base must also better be at the end, so the block can fall. So the base must move A plus B, and in t seconds, the same as the block takes to go from the center to the end. And this is a worst case scenario. The acceleration must be bigger than this one. So this is the minimum acceleration. Well, if you like this video, please consider subscribing. It is very important. And more important than this, I need your thumbs up, because this is the only way that YouTube put this video to more people and makes things happen. So thank you very much for your time. I hope you have enjoyed. If you think this video was enlightening for you in some way, so please give the like, so more people can have access to this on the internet when they look at the internet. Thank you very much. I look forward to see you next time. Bye bye. Have a wonderful day. Bye bye.